Can you recall how your day started? You were probably greeted by a warm home, a hot shower, and hopefully a charged cell phone. Every day, these luxuries are only possible because of an invisible network acting as the arteries of our society. There are pipelines. But as Canada transitions to clean energy, like hydrogen, pipelines must face our harsh climate on top of tougher operating pressures. The industry is demanding tougher, safer steel. To survive these extremes and protect our way of life, we must master how we engineer the pipe itself. So now picture a factory floor with a set of machines over 1,000 feet long that gradually roll a flat sheet of steel into a tube. The two edges come together like a zipper into a weld box where we heat them up with high-frequency electricity, much like an induction cooktop. This is electric resistance welding, or ERW. For scale, nearly half of all tubular products in the world are made using ERW. Now, it sounds high-tech, but in reality, this billion-dollar industry relies less on science and more on a mystic art practiced by operators like Joe the welder. From experience, Joe knows where to set the process styles to get things looking just about right. Consequently, when we want to weld new high-strength steel, it's a costly game of trial and error. A single test weld on these massive pipe mills costs around $10,000. For decades, we have not understood ERW well enough to reliably expand its use. My research models the physics of welding and heat transfer to translate Joe's experience into predictable engineering precision. To do this, I'm partnering with industry to introduce a new concept called the weld point location. As steel moves through the weld V, that high-frequency electricity does two things. It melts the edges, and it generates powerful magnetic forces that push on the molten edges. These forces gradually expel molten steel out of the V, eroding the edges before they actually touch. This ultimately determines the weld point location. Failing to control this erosion creates an unstable weld point, which has already been linked to weaker weld seams. So, when Joe was tweaking the process styles like power and speed, he was actually controlling the weld point. My research uncovers and maps the physics behind these process styles so industry can stop guessing and start predicting exactly how the process will behave. I've harnessed these physics into simple engineering design rules that practitioners are already using, valid for any pipe mill, for any metal alloy, for any application. With these physics-based tools, industry can finally adopt advanced materials without fear. And in doing so, we ensure that the invisible seam at the heart of our energy network is safe, robust, and ready for the future. Thank you.